This is the fourth and final section of the elastic strings and springs chapter, and this is just looking at problems involving elastic energy. So there isn't any new content, so let's think about what we've learned before to help us answer these types of problems. Well, we know about kinetic energy, and the way that we work that out is we need to know the mass of the object, and that's going to be half mv squared or u squared. We know about potential energy, so with potential energy that's mgh, and h is the height above the ground, or the point that we've set as 0. And now we introduce this elastic energy, okay, which is elastic potential energy. Okay, so this is when we will get this stored energy when a spring is compressed or stretched, or when a elastic string is stretched. We have this stored energy, which is elastic potential energy, and that is lambda x squared over 2L. Now these energies here, the total of all of these energies in the system will remain constant. So total energy remains constant unless we have some work done against friction, unless there is work done against friction. So if there's no friction in a system, and it's normally friction which is going to cause the loss of energy, then if there's no friction, then the total energy within that system will remain constant. So the total of the kinetic energy, potential energy, elastic potential energy, they will change, they will go up and down, but the total of them will remain the same. So we're looking for this, this and this staying as a constant. And if it doesn't remain as a constant, it goes down. That's because there's friction and there's going to be work done against friction. And remember, the way that we work out work done against friction is we can do force times distance. So I'll just put force times distance here. Okay, so a light elastic string of natural length 1.6 meters, that's L. Modulus of elasticity 10, so that's lambda. One end fixed to point A on a smooth horizontal table, so that's going to mean no losses of energy. Yeah, because there's the other thing would be air resistance, but there's no air resistance in this question. Particle of mass 2 kg. Okay, so there's our value of m is attached to the other end of the string. The particle is held at point A and projected horizontally along the table with speed 2 meters per second. Find how far it travels before first coming to instantaneous rest. So in other words, when the velocity of the particle becomes, or the speed of the particle becomes 0 meters per second squared. So if we were to draw what's going on here, so our string is connected at this point here, which is called the point A, and so it's actually projected from A. So imagine the string all squashed up there, and it's at A like this, and it's projected at 2 meters per second like this, and we want to find a point where it's going to end up at 0 meters per second. Now what's going to happen as it's projected, it will get to a point where it's moved a distance of 1.6 meters. Okay, that's when the string becomes taut, and then it's going to keep on carrying on like this, and this is where the string moves a distance further than its natural length, so it's an extension of its natural length, and it's in this part where it begins to store elastic potential energy as it begins to get stretched. So beyond this point here, that's when the string gets stretched. So string gets stretched beyond this point. Beyond this point. So yeah, it will move 1.6 meters. It won't lose any velocity because the surface is smooth. It won't lose any speed because the surface is smooth, and then it will carry on moving for X until it stops, and then at that point the string is going to want to fling back. So it's going to move like that. It will slow down as the string gets stretched, and it's going to get to that point, and then at that point it's going to want to go back, and then it'll probably go back. It might hit the wall, or it might come to rest at some point before it hits the wall, something like that. So imagine like an elastic band, and you fire it away from there. It gets to its natural length. So here you would see the elastic band or the string straight, then it would extend, get to this point, reach its limit, and then go back. Right, so the first thing is that there are no losses of energy in this system. We said that already. No losses of energy. And the only energy in this system is going to be kinetic energy and elastic potential energy. So since there are no losses of energy, any loss of kinetic energy is going to be equal to the gain in elastic potential energy, because as that string gets stretched, it's going to start storing this elastic potential energy. So let's first of all work out what the loss of kinetic energy is. Now the speed goes from 2 to 0, so it's lost 2 meters squared of speed. So using half mv squared, I have half times by the mass, which is 2 times by 2 squared. So that gives me 4. So 4 joules of kinetic energy is lost. How much elastic potential energy is gained? So we'll use lambda x squared over 2L. Lambda is 10. The extension is x. And natural length 2L, 2 times 1.6. Okay, so if we work that out, 10, basically 10 divided by 3.2, and we get 25 over 8 x squared. So 25 over 8 x squared, and that's joules, so we can make those equal to each other. So 4 equals 25 over 8 x squared. So that's 32, 4 times 8, divided by 25 equals x squared. So that means that x equals the square root, and it's going to be the positive square root because it's a length of 32 over 25. Let's work that out. Root 32 over 25, and we get 1.3137, like that. Now remember, this is just the length x, the extension. In the question we need to work out what this complete length is here. How has it gone from A? A is here, and we want to know how far it's got to that end. So that means we need to add together our x and 1.6. So if we add 1.6 to that, not 6, 1.6, we get 2.73. That's 3 significant figures. So I can finish off by saying it travels, or the particle travels 2.73, that's 3 significant figures. That's meant to be meters there. 2.73 meters from A. There we go. So that is done. Okay, a particle of mass 0.5 kg, because there's our mass. It's attached to one end of an elastic string. The natural length is 2 meters, so there's L. And modulus of elasticity is 19.6. Okay, so that's lambda. The other end of the string is attached to point O. The particle is released from point O. Find the greatest distance it will reach below O. So here we've got something where something is dropping. Right, so let's draw a diagram. Okay, so here's the point O here. We've got this elastic string that's all bunched up here. So that's meant to be the point O. So maybe I'll draw it so it's a bit further up. But yeah, all your string is all bunched up there at the top, like that. This particle of 0.5 g, it's released from rest, because it's just dropped, it's not projected down. Okay, and then this particle is going to drop. It's going to drop to a point where it's got to 2 meters, and then the string will be taut. Okay, so this distance here is 2 meters, and when it gets to this point the string will be taut, but it will carry on moving. Okay, string taut, that'll be the first time it becomes taut. Then it will carry on moving like this, and then, well, it looks like the particle's got bigger, it hasn't really. Then it will get to a point where the string is completely stretched to its limit. For this question, it will be 0 meters per second here, and then what will happen is the string will basically use its stored energy to fling the particle back up again. So it drops its natural length, then it keeps on going and it gets stretched, and then it will get to a point where it flings back up again. So that does mean this distance here is x, its extension, and we want to find the greatest distance it will reach below O, and the greatest distance it reaches below O will be 2 plus x. Yeah. Now you'll see that the velocity or speed at the start is 0, and it finishes at 0. So that tells us that there's actually no change in kinetic energy. So we won't be using kinetic energy in this question because it goes from 0 to 0. But there will be a loss of potential energy because it's dropping down. But there will be a gain of elastic potential energy, and because there are no other losses, they will be equal to each other. So to work out the loss in potential energy, mgh, that will be 0.5 m times by g times by h. Now what height has been lost? 2 plus x. and the potential energy that's been gained, so lambda x squared over 2L. So that will be 19.6 x squared, which is the extension, over 2L, so 2 times 2. Right, so let's make those equal to each other. Like that. So this is now about working out what x is. So we will times both sides by 4. So we'll have 2g 2 plus x equals 19.6 x squared. We will expand a bracket, so we get 4g plus 4gx equals 19.6 x squared. This is going to be a quadratic then, so 19.6 x squared minus 4gx minus 4g equals 0. Now if we divide everything by 9.8, or we divide everything by g, fortunately for us, 19.6 is g times 2, so we get 2x squared minus 4x minus 4 equals 0. So the rest now is just about factorising that. Actually, we can then divide everything by 2, makes that even easier. So then we get x squared minus 2x minus 2 equals 0. I think I can factorise that. So x minus 2 and plus 1. Yep, that works. So that means either x is 2 or x is negative 1. So obviously we can't take the negative answer. So if we've got x equals 2, then that means, and let's write it here, right, since x equals 2, the greatest distance is 2 plus 2, which equals 4. So its greatest distance will be 4 meters below that point O. Okay, a light elastic string of natural length L, or 1, sorry. So L is 1. Modulus elasticity is 10. 1 is attached to a fixed point, and a mass of 2 kg this time is attached to the other end of a spring and is held at point B, which is 0.8 meters vertically below A. The particle is projected vertically downwards from B with speed 2 meters per second. Find the distance it travels before first coming to rest. Yeah, so when the speed is 0 meters per second. So let's draw a diagram. Let's do that over here. So this is a hanging spring in this question. Okay, so something like this. And we have this mass of 2 kg here, and this is projected downwards at a speed of 2 meters per second. Okay, now a couple of things to mention. I didn't see this bit, or maybe I didn't underline that. So point A is at the top, and then this mass is at point B, which is 0.8 meters below A. Now the natural length of the spring is 1 meter, which means this spring is already in compression. Okay, so spring is in compression. Yeah, so not only is it in compression, but it's also projected downwards as well. So what will happen is it will move down to a point of 1 meter below where it was. So it will move down 0.2 meters. Now when it's at this point, the particle will be at its natural length. Okay, so here we have its natural length, L, and then it's going to keep on going down once it's past its natural length, because it's still releasing its elastic potential energy, to a point where it stops moving. There, and this extra distance, as we've called it before, this extension is going to be x, and we want to find the distance it travels before coming to rest. So not the distance from A, just the distance that it travels. So this is going to be that 0.2, the distance that it travels, 0.2 plus x. So it's going to be this bit here. Right, so you'll notice in this question we actually have kinetic energy, potential energy, and there's going to be some stored or lost elastic potential energy. So there is going to be a loss of kinetic energy because it's going from 2 meters per second to 0 meters per second. So the loss of kinetic energy using half mv squared is going to be half times 2 times by v squared, which is going to be 4 joules. There will also be a loss in potential energy because it's losing height. So remember that's mgh. And it's losing a height of 0.2 meters plus x, or 0.2 plus x meters. So that's that purple line that I drew, because remember it's starting at 0.8 meters compression. So it's 0.2 meters of compression that it needs to overcome, and then it needs to keep going, and that's going to be its extension. That's going to be 2g times by 0.2 plus x. So I might want to tidy that up before I use it. So that'll be 0.4g plus 2gx. So I'll probably use that in a minute. So we've got a loss of kinetic energy, a loss of potential energy, and that will be equal to the gain in elastic potential energy. Okay, gain in elastic potential energy. So let's write down what that's going to be using lambda x squared over 2l. So that's lambda is 10, our extension is x, and the natural length is 1, so 2 times 1. So that's just going to simplify to 5x squared. So our losses are going to equal our gain. So a loss in KE and PE equals gain in elastic potential energy. So now we can write, and all of these are joules by the way, and I put joules just for KE, but they're all joules. So that's going to be 4 plus 0.4g plus 2gx equals 5x squared. We can rearrange that to give us a quadratic. Well, it is a quadratic, just needs rearranging. So 5x squared minus 2gx minus, and then 4 plus 0.4g, like that, equals 0. Now from this point I could actually use the quadratic equation with a equal to 5, b equal to negative 2 times 9.8, and c equal to negative 4 minus 0.4 times 9.8. Yeah, but I'm actually just going to use the calculator to work out the solutions. As I said, you could use the quadratic equation, but we've got our calculator to do that. Just as a reminder, if you're going to do that, you want menu and A, then you want number 2 for polynomial, and you want degree 2, and we type in the coefficients, which are going to be 5, then negative 2 times 9.8. We can actually just type in the calculation, it will work out for us, and then negative 4 minus 0.4 times 9.8, which is negative 7.92, and it will tell us that we will get x equal to 4.28929, then the other value of x is negative 0.36929, like that. Okay, so the distance is going to be the one where we get x is positive. Now remember, we need to add 0.2 to our answer of x, because x is just the extension. And if we add 0.2 to our answer, that's going to give us 4.48929, like that. So we could write down the distance travelled equals 4.49. Now I suppose because we've used G to 2 significant figures, then our answer should be, strictly speaking, to 2 significant figures 4.5, but I'm sticking with my 3 significant figures, so 4.49 is that distance travelled before coming to rest. Okay, a light elastic spring of natural length 0.5, so there's L. The modulus of elasticity is 10, and one is attached to a rough horizontal plane. So if something is rough, it doesn't mean that the total energy remains constant. There is going to be a loss of energy due to friction. So we need to bear that in mind. Total energy doesn't remain constant. There's going to be a loss. The other end is attached to particle P of mass 0.8. The coefficient of friction between the point and the plane is 0.4, so there's my value of mu. The particle initially lies on the plane with AP equals 0.5. Okay, so initially it means that the spring is neither in compression or extension, it's at its natural length, because its natural length is 0.5. So that will be worth bearing in mind. And it is then projected away with speed 2 meters per second away from A along the plane. Find the distance moved by A before it comes to rest, which means then the speed becomes 0 meters per second. So let's draw a diagram of what's going on here. So there's my thing that it's connected to. Here's my rough horizontal plane. It starts at its natural length. Okay, so here's my fantastic spring here, like this. And the mass here on the end of 0.8 kg, and it starts, its length here is 0.5 meters at the start of this, like that, and then it's projected away this way at 2 meters per second. Okay, and we want to work out when does it come to rest, like this. So this will move like that until it comes to rest, and then at that point it sort of pings back and wants to move back to its original position. Now we have friction going this way, which is mu r, like this. That means we need to find r, and so we want mg here 0.8 g. So this involves resolving our forces as well. So if we resolve vertically, we'll have r equals 0.8 g. If we resolve horizontally, then mu r is going to equal, mu is 0.4, so 0.4 r, which gives us 0.32 g. Now, just as in the previous questions, we're going to call the distance that it's moved here, so this will be the extension of the spring, and this is the pure extension because it starts at its natural length of 0.8, and because we're dealing with energy rather than forces, there's going to be work done. So the work done against friction, so this is going to be equal to the energy that's lost. The work done against friction is force times distance, so that's going to be 0.32 g times by a distance of x. So any energy that's lost is going to be 0.32 gx. Okay, so we can write down here energy lost equals work done against friction. So we know the work done against friction, we just need to work out what energy is lost. Now in this case we're going to have a loss, let's write this down, so we're going to have a loss of kinetic energy, yeah, but we're also going to have a gain of elastic potential energy, but the loss of kinetic energy is going to be greater than the gain of elastic potential energy, so we need to do the loss of kg minus the gain in EPE, and that will give us our total losses. So let's start by working out the loss of kinetic energy. So half m v squared. Okay, so there's our loss of KE. Okay, but there's going to be a gain of elastic potential energy, so that's going to be lambda x squared over 2 times the natural length, so that's 2 times 0.5. Okay, so this is our gain in potential energy, and that's going to equal the work done against friction, which is 0.32 0.32gx. So we're now at the point where we can solve to find x. So if I look at the first bracket, so half times by 0.8 times by 2 squared, and I get 8 over 5, which is 1.6. So now I've got 1.6, and then I need to subtract basically 10x squared. Yeah, 2 times 0.51, yeah, so minus 10x squared equals 0.32gx. So we've got a quadratic again like before. So 10x squared, if I move that over, plus 0.32gx minus 1.6 equals 0. Now, if I was going to be using the quadratic equation, I would have a equal to 10, b equal to 0.32 times 9.8, and c equal to negative 1.6. I'm just going to use the calculator to work out what value of x I get. So again, menu and a polynomial degree 2, and my coefficients are 10, 0.32 times 9.8 and negative 1.6. Now I get a value of x either equal to 0.27283 like that, or the other value of x I get is going to be negative 0.586 blah, 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 like that. So because I want to find the total distance, that means x is going to be positive, so the distance travelled is going to be that 0.27283 that I want to add on. Well, actually there isn't anything to add on, is there? It's just that value of x. Yeah, there isn't any other distance. We don't want to know the distance from A, we just want to know the distance. So actually that just is going to be our final answer. So 3 significant figures, as I said, strictly speaking 2 significant figures because we're using G, 2 significant figures. That distance is going to be 0.273 meters, and that's if you're using 3 significant figures. If you're using 2 significant figures, it will be 0.27. Okay, so you should now be able to do exercise 2D on pages 54 to 55. So remember, total energy is constant, total energy constant, unless there is work done against friction, remember the energies we're talking about are kinetic energy, there is potential energy, and there is elastic potential energy. So these are all the energies that we've done. If there is any work done against friction, then that work done against friction will be the force of the friction times by the distance, and that force of the friction, it may be a constant, it may be given in terms of mu r, in which case you will need to work out the normal reaction and just multiply it by mu, the coefficient of, forgotten what it's called, so many coefficients, the coefficient of friction, yeah, so normal reaction coefficient of friction. Now you just need to be aware, watch out for springs or strings that don't start off on their natural length. That needs to be included. Okay, so watch out for strings or springs not initially at their natural length, because that might be something that you need to add on or subtract from the distance that has been moved.